Hello. This video lecture is about transmission lines. Transmission lines occupy an interesting way station in learning about applied electromagnetics. Basically, electrical engineers start learning about circuits and circuits made up of discrete components, and eventually you'll have to move on to analyzing, thinking of system operation in terms of waves and fields. Transmission lines fall somewhere in middle that continuum, where you can use some form of circuit analysis to help you understand the system. However, you cannot use a lumped circuit analysis that we are used to in basic electrical engineering. I will start by quickly going once again into the approximations that allow us to think of electrical systems as circuits. And going from Maxwell's equations, any electrical system is some region in three-dimensional space, and to do a full analysis, an exact analysis, you have to solve for the E and the B fields with inputs as current or charge, for example. And this is doable nowadays using computers. However, there is still a limit on how big a system you can analyze even with modern computers. Additionally, when you use field analysis, you lose a little bit of physical understanding, simplicity of physical understanding that comes with circuit analysis. So, circuit analysis gives you simplifications. Once we know the behavior of discrete components, we can arrange them in any form and use the laws of circuit analysis to understand how they behave. If you were to do a full field analysis of an electrical system, then the exact spatial distance between them, all these things will start to matter. I have another video where I go into a little bit more detail into how you can derive Kirchhoff's circuit laws from Maxwell's equations. So please have a look at that. I wanted to quickly revise, however, the derivation of Kirchhoff's voltage law. And when you examine that in detail from the perspective of Maxwell's equations, you come to understand where exactly the laws of circuit analysis break down and how to build better circuit models for your system. Specifically, you can build circuit equivalents for any system. However, the complexity of building an accurate circuit representation increases generally as your frequency of operation increases. So we have to go from simple component level circuit description to a more involved distributed circuit representations. And transmission lines serve as an example where you encounter this approach of building a distributed circuit representation of an electrical system. There are a lot of resources tell you where transmission lines come in, so I'm not going to go too much into detail on that. However, I just want to mention that we consider here in this theoretical analysis a very simplified representation, two conductor lines. The generality of transmission lines goes much beyond this, and it occurs in all kinds of circuits where signals are usually transmitted over a large enough distance. This includes all kinds of communication systems, antenna feeders, radio stations, cell towers, and also, for example, radio frequency integrated circuits where such things have to be done. So quickly, we take a loop as shown here of area S bounded by a closed curve C, and you must be already familiar with this. When we apply the Maxwell-Faraday equation to that, then we end up with the statement that the sum of potential drops around the loop, it's the left hand side in this equation, is actually equal to the surface integral of magnetic flux that is going across that particular enclosed surface. In order to see, make it a little bit more clear, first of all, I want to see that this term is not zero in general, and you can only neglect it if this term is small compared to the sum of terms that make up the left hand side term. Remember, left hand side is the sum of potential drops across components. So if this component has to be far small compared to each of those terms in order for your analysis to be more and more accurate. Let us break this integral in this way. So I have broken the flux, magnetic flux, which is in general a function of x and y, x, y, and z, into three components. One, I've broken it down to be self. This is the contribution by a particular component. And the second one is the externally imposed magnetic field. The last one is the field induced at one component by a distant component, by a neighbor or a farther neighbor or near neighbor, for example. So the field created by the component itself is easily incorporated in the self-inductance by assigning a self-inductance to that component. The EMF has to be calculated depending on how your external field is. In many cases, there may not be an externally imposed magnetic field. So in that case also, you don't need to worry about the EMF. The last term, however, is the one that is difficult to incorporate because it really depends on what is the exact relative arrangement of both of these components. Let us see if we can, under what conditions we can approximate this term away. Is there a condition under which we can neglect the last term, the term that is coming due to the mutual magnetic fluxes? And in order to do that, what we do is we express the mutual magnetic field B mut in terms of some vector potential A. And by doing that, we can show that this term is going to be proportional to LC by lambda, where LC is the circumference of the loop and lambda is the frequency of the signal. So this derivation is of course conducted in a time harmonic approximation, and lambda is the frequency of the excitation source. So now we see that on the left hand side, the sigma voltages, that term is incorporating regular potential drops as well as the potential drops due to self-inductance, and the mutual inductance term is going to be proportional to the circumference of the loop. If you manage to make the circumference of the loop small enough so that LC by lambda into the A average, that entire term has to become smaller than the individual terms in your voltage addition. In that case, we can see that this mutual inductance term, this can be neglected. Once we can neglect this, this is very nice because this now You don't really need to know the exact spatial arrangements of these components. As long as your loop is small enough, this term is seen not to introduce a huge error. This is where the entire idea of making a distributed circuit representation comes in. Imagine you have a physical system, and if you want to create a circuit representation of that system, you need to ensure a few things. First, of course, you need to calculate all the component values, the inductance, the resistance, and so on. But more importantly, you need to make sure that your circuit has loops whose circumference is smaller than lambda. So for example, if we take the case of two wires that are parallel to each other, which are transmitting a signal from one end to another end, if we were to think of this system, now this system will have mutual inductance that arises from the magnetic fields created by the currents flowing in this wire. As well, there is capacitance between the two wires. There would be additional leakage and Joule heating related resistance and conductances as well. How exactly will we assign a circuit model to this system? You cannot assume just one inductance, assign just one inductance to the entire wire. Reason is then the loop size, in your case, will not obey this approximation. So, if we have to construct an equivalent circuit for this system, we need to create multiple such loops, or we need to create for every small element in this system an equivalent circuit. As long as that element is small enough, and for each element you construct an equivalent circuit, then if you put them all together, you have a circuit representation of your system, which will also be accurate. And this is what gives rise to the ladder network that you encounter in transmission line analysis. Notice that when we construct a circuit representation, we assume that all these components are ideal components. So R is an ideal resistor, meaning it does not have any capacitance or inductance associated with it. Of course, how exactly do we calculate these values? For that, you need to really solve for the fields again. Luckily, what we find out when we proceed with the analysis of transmission lines is that exact calculation, the exact calculation of R, L, G, C parameters is need not be required in all cases. Sometimes you can simply measure things and deduce these properties. However, I do want to point out that if you want to calculate them exactly, then you do need to do field analysis. Alright, so thus we will take a little portion of this circuit and let us examine that carefully. This little portion of the circuit is located between Z and Z plus delta Z, or Z and Z plus delta Z. It is located somewhere in the middle of the transmission line, as seen here. And I want to also point out that the inductance and all these components that we assign to that little portion transmission line are expressed as R times the length. So the RLGC parameters that we see here are per unit length quantities. So you could calculate the entire inductance of the whole line, then give a per unit quantity here. L delta Z is the total inductance of that little component. L is the per unit inductance. Again, these have to be calculated by doing a field analysis. But for now, let us say somebody has done this and we know these values. Question is, what next? I also told you that the entire transmission line is now represented by a ladder network, seen here, composed of these little elements, one next to each other. And we are also guaranteed that each of these little loops here have the necessary circumference. The circumference is small enough, and so we can apply now the circuit laws KVL and KCL to each of these loops. And because we can do that, we can thus analyze the entire transmission line in terms of this distributed circuit. And to do that, we need to do a few things. First, we need to label all the nodes, which is what I've done here, A, B, C, D, E, F, these nodes. And because we're going to apply Kirchhoff's current laws and Kirchhoff's voltage laws to this network, we're going to have to fix the sign convention. So I'm going to fix the sign convention in this way. First of the voltage, as you can see how I have fixed the sign convention. So at AB, I have this is my polarity, and also I need to fix the convention as to where in which direction current flowing in this capacitor and conductor are to be considered as a positive direction. So that is the first thing I need to do to analyze this circuit. Additionally, let us quickly recall what are the current and voltage relationships that each of these idealized component satisfies. For the resistance and conductance, the leakage conductance, it's easy. It's simply Ohm's law. And for capacitor, the current is C dV by dt, and the voltage across the inductor is L di by dt. So we're going to use this relationship. One more thing that really is helpful in doing this derivation is to recall the Taylor expansions. So the voltage at Z plus delta Z as a function of time expanded across Z is given as VZT plus the first partial derivative of V with respect to Z into delta Z. Now, plus, of course, there are some error terms here, which we are assured is of the order of delta Z square, or even delta Z cube. Now remember, delta Z, as it goes smaller and smaller, these error terms are going to matter less and less, and so we can neglect them. So this is the Taylor expansion. It holds provided your delta Z itself is reasonably small compared to lambda. Now here is again the fixing the sign conventions of each of the components. As you can see, the blue color showing how the voltage polarities are fixed for the components. The green color is showing you what is the direction of currents that I'm assuming here. If the actual current turns out to be negative, then it will give you a negative value, right? So I just have to fix the convention first and then work out the KVL. Right. So after you do that, the first thing we do is calculate the current through. First we do KCL applied at the C bar E node, and current through CD is given by this term here. And notice here that the voltage that enters into this is actually voltage at Z plus delta Z, not the voltage at VZ. And so this causes some confusion. However, once again, if the Taylor expansion is good enough, that means we need to retain only terms until delta Z, then this approximation, I can always approximate this as C delta Z into dv by dt, where the voltage is at z, right? So you see this subtle step here, right? So this will hold true provided delta z is smaller than, far smaller than lambda. Same thing happens through the current at through EF. Again, Vz plus delta z plus delta z appears in those terms. However, we're going to approximate that by Vz comma t. Once we collect these two terms, we can now apply the KCL to node C bar E, and notice we just equate the outgoing current to the incoming current and rearrange the terms, which will give you equation number 1. So basically, notice that it has terms: partial derivative of voltage is related to the time derivative, the partial derivative of voltage with respect to time is related to the spatial partial derivative of current. Similarly, when we now apply Kirchhoff's voltage law to the loop A C bar E D bar F B A, so basically we go A to C to D to B and A. Instead of C, I'm going to call it C bar E. Okay. Notice, however, that the drop across CD is same for both components, right? It is simply V Z plus delta C. So when we do this, again, we get an equation similar to equation 1, however, with voltages, the spatial derivatives of V instead. Now, you can, in order to simplify this, we need to eliminate I first. And this is a little bit involved here because there are lots of operators and so on. So I tend to use the operator notation here to simplify these two equations. So I can write it as operator R plus L d by dou by dou t operator on I is equal to, so that we can so first it is expressed in terms of these black terms, as you can see here. Then when you assemble it this way, it is easier to see how to eliminate I. The way to eliminate I is to take the z partial derivative of the first term and reverse the order of these two operators. Reverse the order of this operator and this operator. And we can do this because these operators will commute. If you are not familiar with this operator terminology, you can go ahead and do straightforward algebra. You'll also get the same thing. This is just a way for me to quickly summarize this. And after doing all this simplification, we're going to end up with a ugly looking partial differential equation which contains only a VZT. It has lots of terms. There are z squared partial derivatives, second partial derivative with time, first partial derivative with time, and so on. What it actually denotes is a lossy wave. So this is the wave equation with the loss terms, the damping and so on. In order to make it a little bit more comfortable to look at, we are going to switch to a time harmonic representation, whereby we're going to replace the voltages VZT, for example, as a we're going to basically do e to the power j phasor notation, assuming that only frequencies omega are present. This amounts to considering the transmission line to be operating in a steady state. If you want to do transient analysis, you have to once again go back to this long equation. Okay, when you do the time harmonic representation, remember the term derivative simply becomes a j omega, and the partial derivative with respect to z becomes a single ordinary derivative with respect to z. Doing that gives you basically, I'm going to take this equation 3 and apply these modifications, and after some algebra you're going to realize now the equations look somewhat nicer. They're just second partial derivatives, not partial, second order differential equations, simple ODEs. So d square by dz square, v as a function of z. Note, however, the v and I now are phasor quantities, which have a e to the power j omega t time dependence. J omega t time dependence. Now, you can see that both the voltage and the current satisfy the exact same equation, and this actually turns out to be the wave equation, the time harmonic wave equation, if you will. And the parameter gamma includes all our RLGC parameters, and gamma is of course a complex number because you're taking the square root of a complex number, and the gamma is usually called as a propagation constant, and alpha is the attenuation constant, and beta is a phase constant. Now, in order to solve this equation very quickly, you can use the D notation, right? And so you just basically realize that the solution of this differential equation is nothing but a e to the power plus gamma z plus b e to the power minus gamma z, where a and b are obviously free parameters. They change depending on what the exact conditions are at the either ends of your transmission line. Because we are representing the solution for a voltage, we will usually, instead of using A and B terms, we can simply do V plus and V minus to signify that it's a voltage. So that's it. So this is what leads us to the expression for the voltage, steady state voltage on the transmission line in general, where any condition is V plus E minus gamma Z plus V minus E plus gamma Z. If you want to see physically what exactly does this mean, then of course you have to multiply this by e to the power j omega t and take a real part. When you do that, you will see that the first term here represents a wave that is traveling in the positive z direction, and the second term represents a wave that is traveling in the backward or the minus z direction. In general, these waves are exponentially decaying sinusoids. So if it's going in the plus z direction, it is going to be decaying in the plus z direction. And if it's going in the minus z direction, it's going to be decaying in the minus z direction. Again, from one of the equations above, we can now try to write the expression for the current. And after some algebraic simplification, we end up with the expression number 5, as seen here. And there is a difference. There are two differences to note. The biggest difference, of course, to note is the signs of this thing. The plus here and a minus, plus here in the voltage, and there's a minus in the current. What does that mean? So I'm going to talk about that a little bit later, but bear that in mind. And second thing you see is that the current, the I plus for the current, if you will, the constant A and B, are given by V plus by ZC, and other current is V minus by ZC. So now we only have two constants, V plus and V minus. If you solve for those two constants, you have the voltage wave as well as the current wave expressions. The constant ZC has the dimensions of an impedance, and it is called the characteristic impedance of the transmission line. So to summarize, this is what we have done. We know that the expressions for the voltage and current are given thusly, where gamma and ZC are properties of the line, and they will never change at all, regardless of what you're doing at the source or the receiver end. Right, so here's your transmission line. It's a two-port system, port 1 and port 2. The V plus and V minus are determined by the source and loading conditions. Gamma and ZC are properties of the line. A very quick physical interpretation again of these equations. The voltage wave and the current wave, two terms are here. Notice the polarity that is assigned to the voltage waves. Even when it is going backward, it still has the same polarity as the forward traveling wave, just the directions are different, right? That is why the expression is V plus something plus V minus something. In the current, however, something to recall is the current has a return term, right? So if you go back, I'm going to go back to when we derive this here. Right here, we have to notice that this is a return current, right? This is always going to be equal to the top current, this current, this return current, and this comes from Kirchhoff's current law. Assuming CEDF is one big node, you see how this comes about, right? So this is how it comes about. This return current is going to be there for both the forward traveling current wave and reverse traveling current wave. So that the current going through dB, that is not the backward current. Bear that in mind. That is the return current. That's return current is not the same as backward traveling current wave, right? So each even forward and reverse traveling currents, both of them circulate throughout the line. So the forward traveling one will have both these components. Excuse me. Right. The forward traveling component will have this main current and a return current, right? And the reverse current will also have a similar one, except the polarities are now going to be reversed. Right? So the polarity for the backward current wave is opposite of that. That's why we have a minus sign in the equation. So in other words, the forward traveling and the current traveling waves on the top conducting line are going to subtract each other, right? So on the top line, there's going to be a term due to the forward wave and a term due to the backward wave. On the bottom line also, we're going to have a term in the forward wave due to the forward wave and a term due to the backward wave, and they're going to reverse, right? Yes, so the voltage wave is easy. The current wave, however, it's important that for you to realize the difference between return wave and the main the wave itself. All right. So until now we have been general, but if we consider a line that is lossless, in other words, the R and G terms are 0, then we get further simplifications of equation 4 and 5, in that we're going to replace gamma with J beta. That's the only difference. In most cases, we consider the lines as approximately lossless. This remains true provided you don't consider too long a line and so on. This concludes portion 1 of this video.